Thanks for attending my talk today. So as he just introduced me, I'm a data advocate and partnership lead at SuperAI. We actually got a booth outside if you're interested in learning about what we do. We provide training data management platform for computer vision. And as an advocate and partnership person, I'm basically just, produce a lot of content, go to talk like this, conference like this, and help lead some of the partnership initiatives for companies to partner with. Super exciting initiatives to kind of push forward the ML infrastructure ecosystem. So at the summit today, I will talk about data-centric computer vision and DataOps. And the term data-centric computer vision that I put here in the slide basically got inspired by the movement of data-centric AI, which, as it put here in the slide, is the process of building and testing AI system by focusing on data-centric operations rather than model-centric operations. So essentially, you want to focus on some of the procedure like data cleaning, data cleansing, data augmentation, etc. However, because it's pretty a new movement, there are so many existing challenges, right? With iterating on data set rather than iterating on improved model performance. Because coming from a research background, you're probably more familiar with doing model architecture, model design, that kind of thing, rather than working with the data. And therefore, I argue that there is this increasing needs of doing data ops for unstructured data that can basically systematically orchestrate some of these data-focused tasks that we need to focus on. So the next slide is kind of my proposed stack for how data ops might look like for building modern computer vision application. So let's unpack this slide real quick. So the DataOps pipeline is the other part in the gray box, as you can see. So the first block is data acquisition. And data acquisition is the idea of you want to acquire data. This is the first step that you want to do when you start any CV project. And within data acquisition, there are three separate tasks. So there's data collection, and there's both the physical and operational consideration with this, right? Ranging from where to collect the data initially to how much to collect it. And ideally, you want to collect the data that can align with the business feedback. After data collection, you can also try out synthetic data generation. So this is basically you can use techniques to generate synthetic data, and there's some different use cases ranging from self-driving vehicle to life science, etc. However, getting this synthetic data requires a lot of training data and compute, and also you have to deal with some of the more fundamental research questions like how to negate biases, how to tackle memorization, right? And then the third approach is called data scavenging. And so the idea here is basically you can scrape the internet, or you can also use open source data set like Cargo or academic benchmark. So that's the first block called data acquisition. The second block in the green box is data labeling. And this is an industry of its own because you have to answer so many different questions, who should label the data, how should the data be labeled, and what data should be labeled. And indeed, getting data labeling, this step correct is extremely complicated because it is error-prone, slow, expensive, and often impractical. Efficient labeling operations often requires its own lifecycle, specific tooling, versioning system, even qualified person to actually do the labeling, and then also a validation process. So that's the second block. And then the third block is what I call data debugging. So the idea here is want to write expectation tests to address some of the data preprocessing and storage system. And I want to call it unit tests for the data. So they are designed to catch data quality issue before this issue make the way into the DataOps pipeline. The fourth block is data augmentation, and this is a scientific process where you can manipulate the data by flipping, rotation, translation, and grayscaling. Now, in Vision, you can use a lot of techniques to augment your data, but you have to be mindful of some of the things like how to scale augmentation to bigger data set, how to negate memorization, and how to handle some of the biases and corner cases. The fifth block is data transformation, which includes three separate tasks. There's data formatting, which is a small slide of the whole data engineering task where you interface with data warehouse, data lakes, and data lakehouse. There's feature engineering, and this is a concept like feature store, you management of correlation, management of missing records, and going from feature selection to feature embeddings. And finally, you have data fusion, which is basically you want to fuse your data from different modalities, different sensors, and different timelines. Okay. And then the sixth block is data curation, and I think this is one of the most underrated steps within its life cycle because it serves as a liaison between DataOps pipeline and MLOps pipeline. So the idea here is like, because your data set can be very big, very, very, extensive, you need to be picky about what type of data you should pick, for your model development. And concretely speaking, you can do so by catalog and structure your data in a methodological manner. And then after that, you can select the most relevant data that could be useful, for your MLOps pipeline. So after data creation, you go into the MLOps pipeline where you perform all of the model-centric tasks like, model experimentation, model training, model deployment, model monitoring. And then to close the feedback loop between the MLOps pipeline and the DataOps pipeline, you need to detect failures and edge case. So these are the cases that your model makes the fail prediction on, right? And then you want to, collect these edge cases, feedback into data acquisition to generate a new training data set, and that can be fed into the next version of your, system. So it's a very iterative process, and within this last block, you have to do things like drift detection, performance metric monitoring, and data observability. So I hope that this slide can provide you a brief overview of like what are the different tasks involving data that you need to solve, when you designing your computer vision application. And so, with that in mind, let's talk about some of the challenges with actually like implementing DataOps in practices. There are so many different tasks that computer engineers cannot do due to the lack of tooling, time, and data. And I will, go through each of these and illustrate how DataOps can solve this issue. Number one is the challenges with data visualization and feature extraction. So in this slide on the left, you can see it's your typical data set. You're working with any visual images. You can see that there's so many different data types with different colors, different shapes, and different background. And your task as a computer vision engineer is to turn them into the diagram on the right, which entail clean and cluster samples of images, right? So concretely speaking, as an engineer, you're going to go through all of these images, cluster them based on some similarity score, and then you develop models to do this task automatically. Essentially, you need to look at like a lot of images and come up with feature ideas for your model development process. And right now, I could argue that this process is done very manually. The computer vision engineers have to manually visualize each image one by one, go through them with the human eyes, and repeat this cycle multiple times to develop feature ideas. And I believe that your time really can be spent on something else, something that is more ROI focused. And then another thing that the CV engineers are not doing so well right now is training test set split and data curation. So as a machine learning person, you probably understand the importance of like choosing, the choosing and splitting your training set and your test set, right? So the idea is like you want to train your model on your training set, and then you evaluate your model on your test set, right? So just to kind of illustrate with an example on the right here, let's say if you only train your model on the top row with all this red cup, and then test it with only the top row, then your model will only do well on this type of cups, but it will not do so well on these cups on the second row or the third row. And that's why you need to train and test your model in a well-balanced data set with different type of object class, different type of objects, basically with balanced distribution. And however, like due to the lack of tooling, time, and data, right now most of the CV engineers, what they do is they basically train their model on the data with very similar distribution. It's like basically a lot of the same object classes. They randomly sample 10% of that training data, make that a test set, and then test the model on that test set. And as a result of that, a lot of biases and imbalance problem might emerge. Just to kind of illustrate that, this lab diagram here comes from a curation report that our team at SuperPI has created. It is based on the BDD 100K dataset, which is a self-driving car dataset where a self-driving vehicle go around the scene and capture a lot of images on the street. And you can see there's a huge long tail problem, right? So there's, if you take a look at sort of that dark gray bar here, it comes from the original random distribution of objects. You can see that there are many more objects like car, traffic sign, traffic light, and person compared to the rest of the other objects. So if you train your model on this randomly sampled data set, then your model will perform very well on the oversample objects and then perform poorly on undersample objects. And the right side is another example of gender biases. So the activity of cooking is heavily associated with the woman as an agent role, right? And so the model has learned to identify a person who's cooking as female, even though, for example, in this instance, the image is that of a male person. So this is how, like, the issue with unbalanced training test speed can easily lead to bias in the real world. And the last point I want to talk about, as we talk about this workflow, is data-centric AI. So I mentioned earlier in my talk that just to kind of recap it again, data-centric AI is this process of building and testing AI system by focusing on techniques meant to improve and optimize the data rather than the model, right? And at a high level, there are three separate ways that you can, improve your data. And this is coming from an article by the team at Alectio. So the first one is that you can modify your labels. As I alluded in my previous slide, labeling large-scale data set is insanely expensive, time-consuming, and error-prone. Under certain conditions, you can rely on like pre-trained machining model, or you can utilize quickly supervised approach to like generate label faster, if possible. And you can also use a human in the loop. For instance, you can use human in its process who can fix labeling errors and imperfection. Besides that, you can also modify an existing data set by using active learning to decide what data samples to be removed and to be augmented. Then finally, this might seem pretty obvious, but you can improve your data set by adding more data, preferably in a strategic manner. So an unfortunate thing is that, guiding the collection or the generation of new data in a way that positively impacts the learning process of the model and makes it more efficient is a topic that sadly does not get enough attention from researchers currently. And therefore, I would argue that due to the lack of tooling, time, and data, most of the engineers, the civil engineers now, they decided to tweak the model when the models underperform rather than tweaking the data, just because they don't have framework or tooling or data, to do all of that. So from that research and understanding some of these industry-wide pain points, our team at Superb has just been working hard to kind of deliver some sort of solution to tackle these different challenges. And recently, we are working on this new product called DataOps, which essentially is an automated data quality assurance and curation platform that empowers the computer vision engineers to explore, evaluate, and improve the vision-based dataset more easily while reducing the labeling, QA, and engineering time being spent. And the product is still in beta, but it consists of, at the high level, it consists of some of these features. So mislabel detection, essentially, it can detect misclassified bounding boxes and segmentation annotation in images. Edge case detection, it can find and mine some of the edge cases in dataset to prioritize for labeling and constructing training and test set. Auto curation can automatically curate test and training set with matching data distribution. Then image similarity search that can use embeddings and to find clusters of visually similar images and objects within the dataset. Natural language query that can quickly explore and find some of the relevant data. And finally, an embedding store that can visualize dataset in a 2D space to better understand the dataset composition and distribution. So that's the high level of some of these features. And I want to double click on maybe 3 or 4 features to kind of illustrate how they looks like as a product currently in betas. And these features I follow the exact same format I talked about before, regarding some workflow pain point without DataOps and see how this can be solved using some of the features with DataOps. So we talked a bit about data viz and feature extraction earlier, right? So with DataOps, you can leverage our embedding store and data visualization on top of that embedding store. So if you're not familiar with the concept of embedding, essentially it's a way to represent information from a high dimensional space into a much lower dimensional space. And you can preserve your relevant information about the sample while drastically reducing the cost of storing and processing the information. So that if you work in computer vision, you definitely need to work with image embedding. That's the way you use to creating your neural networks model, right? So looking at the slide here, given a big cluster of images on the left, an embedding store can cluster these images into smaller clusters of here like occluded images, image behind bars, and then image with various vehicles. So, the idea here is like using an embedding store. You can create embedding for your data set, look at different sections of those embeddings, cluster different images you are looking for, come up with ideas, and then find the patterns for your model development process. And with some of these powerful capabilities in data visualization, you can easily do that. Yeah. This is an example of a workflow with embedding store. So given a set of label data, let's say you want to find only the red cars at night, you're going to use our natural language query. You write a text here on our UI, red car and night, and you perform semantic search for those sample objects. You check out the results, and then you find like the returning images, right? And then you apply the new tags, red cars at night, to those results. So here are some of the major benefits of using a workflow with an embedding store. You can search, analyze, and understand the dataset better. You can train your classes a visually similar subset. So let's say like you have a bunch of images currently being labeled as car, right? You just have a lot of car objects within the images. Maybe you want to be even more fine-grained, you want to go deeper in that. You select a subset of images with police car, right? And then you perform semantic search to find the visually similar images of that, and you apply the new tag by relabeling all the new subset as police car. So you can like change the labeling to make it better. You can also add additional labels, right? For instance, let's say, talking about self-driving car example again, let's say that self-driving car data set only have the objects being labeled, but it does not have the information about the weather condition, okay? So what you can do is you can perform semantic search for the terminology, let's say rainy, okay? So it will return all the image of car driving in a rainy condition, and with that you can apply the new tags, the new labels into those samples. So in the future you know that these are cars driving in a rainy condition. And then finally, you can couple this feature with mislabel detection, which I'll talk about in the next few slides. Okay, so like kind of going back to this workflow with our DataOps, I talked about training and test split a little bit earlier, and now let's go over kind of how we can solve this problem. So to help with the training and test split and data curation challenge, we've been working on this feature called automatic curation. So let's say at the beginning of your model development, you can split your data set into training, validation, and test set. And validation is essentially is similar from test set. It's also being split on a training set. And the idea is you want to use the validation set to like check the progress of your model performance. And then with our curation features, it basically deliberately split these three different sets, right? Training, test set, and validation set in a balanced way, even before you start developing your models. So you can see here, like given the input data, we try to be as balanced as possible to like curate these training, validations, and test set so that they have similar distribution of objects. So when you actually build your model, you know that you are training on, you know that you're training, validating, and testing on a well-balanced data set. Just to kind of illustrate that, this is another graph from our curation report. The y-axis here shows the number of embedded cluster, and the x-axis shows the size of the cluster. And zooming deeper into the x-axis, you can see that the right side contains the more rare images, and then the left side contains of the rare images, and the right side contains of the more commonly found images, right? And so when you take a look at the let's see the dark blue bar here, okay, they've been sampled from the original randomly sampled data set. You can see that you can see that the dark blue bar picks up a lot more of the common images, right? Like the distribution of the number of the clusters that the dark blue bar pick up skewed heavily towards the right side. And think about like if you train your model on this dark blue bar sample data set, it will perform pretty poor on some of the edge cases. And the red bar here is coming from our curated data set essentially, and our curation algorithms try to pick up as many rare images as possible so the model can react and perform well on some of those edge cases. And this slide here shows another example of our curation report from the same data set. So like for some of the object classes that are more common, like car or traffic sign, you can see that there's not so much differences between the distribution of the curated dataset in red and the random dataset in dark blue. But for like the rare objects like bike and rider, you can see that our curated dataset picks out much more of these objects compared to the random dataset. And this is how we choose a balanced dataset for your model training and testing in practice. Okay, taking a look at the workflow with data curation. Given a set of label data, let's say you want your task is to train your model on some number of classes and you require some number of images. You can perform test set curation, as I alluded earlier, and then you check out the results on that new test set. You check out the curation report, and then you apply the tags on the curated data set, and then you can export that new curated data set for your model training process. Three major benefits of using this new workflow with data curation. Better distributed training and test set will lead to better model performance. That's just a fact. So, and secondly, you actually curate the data automatically based on our embeddings instead of relying on like manual label or heuristic, right? And then finally, Super AI, we also have like this automated labeling capabilities where we have technology to automate the process of labeling the data, so you can use data curation coupled with that capability. The idea is like if you already curate a good training and test set, you can easily apply the labeling into that curated data set, and therefore getting a high quality label data set faster. Then finally, the workflow with data-centric AI, we have two features that are personalized for this issue. HK detection, that is more focused for model debugging, and mislabel detection, that is more focused for data QA. So HK detection is an extension of our embedding store features that I talked a little bit earlier. So after you visualize and find the different cluster with similar image characteristic, you can combine them with another feature currently beta. We call it model inference uploading, where you can upload the inferences of your model in production into our platform. You can see which cluster are performing well versus not well. So to be more concrete, take a look at the slide here. So you can see that, like, let's say image in occlusion and image behind bars, it seems to perform not very well based on our model results. On the other hand, our model seems to perform better on the images with various vehicle. And given this insight, you can make intelligent decision on what types of images to collect more. And I didn't include this here in the slide, but we are also working on a new feature called semantic search. So the idea here is like, you want to find more edge cases, right? So you can perform semantic search, which will discover the images with similar characteristics of the edge cases. And the more edge cases you find, the more data you can fit back into your model development, and the better your model will perform on those edge cases. And then mislabel detection is the feature that I talked that would have been developing more specifically for data QA. So it's essentially an auto quality assurance feature that can automate the curation process to make it more efficient. So here this is some of the UI of our current product in beta. It basically tries to source the label data by order of mislabel scores, and then it shows you the images that are likely to be misclassified. So by detecting this mislabel, you can, you know that you can fix this quality, and you can do a few things. First, you can maybe like go back and fix the label on the spot, right? You change the label, or maybe if you don't have the capability to do that, you can put some of the mislabel images back on the queue for someone else to go back and review these labels. Most likely, can be some labeling team, either in-house or offshore, to go back and fix this label. And another part of this mislabel detection is what I call the mislabel detection report. And this report shows the patterns of your data, like classes that are likely to be mislabeled, visualization of different object classes so that you can perform quality assurance on them efficiently. And based on the size and width of your data, you can see how many mislabels are there for each aspect ratio. So essentially, we try to provide a very comprehensive overview of what the mislabel dataset look like, and use this information. You can use them to fine-tune your labeling guideline and understand your dataset better. And just like how I talked about the workflow with some of the previous capabilities, also include this slide on how a workflow looks like with mislabel detection. So, basically you divide the label data into query set and reference sets. And then after that, you export both the query set and the relevant sets. And you run misstable detection on that. You check out the results. You check out the misstable detection report. And then you choose the classes with high likelihood of mislabel. You apply the tags for these classes as being likely to mislabel. And then you maybe you can assign them for relabeling, right? So even before you have to like do the relabeling, even before you have to hire like a labelers to relabel them, you already know that these images have a high likelihood of being mislabeled. So as a result of that, two major benefits. Number one is to reducing manual review and QA time as well as money. And number two is that you obtain a higher quality data set with fewer mislabel. Yeah, so I hope this talk's been useful for you to kind of learn about some of the features that we've been working in-house. But in general, I think that this is a space that requires a lot of intervention and innovation, because I think data-centric AI, data-centric computer vision, DataOps in general still require a lot of thought leadership. And these are just some ideas that our team at Superb has been working on based on our conversation with clients and now communities. But I'm sure people attending the conference might also have their own ideas and perspective. So if you have any question and just want to chat more about kind of your thinking on this topic, I include my email here on the slide. And if you want to try out the product, maybe join the waitlist about the DataOps platform, I also include a tinyurl.com link on the slide, so you can check it out. Thank you so much.
Thank you, James. We can take one question. Tim, right there.
Thank you for a very good talk. I was just curious about your placement of the data curation block at the very end. Mm-hmm. It seems to me that with a data collection where there is an easy source of data, in my case, I've worked with some of the tier 1 automotive companies, and they have literally petabytes of data from their driving fleets. There is never an option of labeling all of that data. So you have to do data curation right between the first two blocks.
Mm-hmm. Yeah.
How would you, is that a fundamentally different type of curation in your mind?
Yeah, I mean, that's basic curation of unlabeled data, right? Yeah. So I think we can talk about curation of unlabeled data and curation of labeled data. I think curation of unlabeled data means like you're working with like sensors and metadata. And so I think it's definitely require a different set of curation approach. So the talk that I give here more focus on curate the data already be labeled. So you have like crowd truth essentially, and rely on the crowd truth to create better sample data set. But for unlabeled data, I would say you probably have to rely on built-in features of like your data storage capabilities. Like if you use any lakehouse or warehouse option, maybe you can configure your data storage to only store the most relevant data at the beginning before even streaming to your lakehouse or your warehouse. And then from there, you can, before the ingestion step, before you ingest that data from that storage into your internal system, you need to do curation. But most of that is going to be very automatic. You probably don't need any human in the loop. Maybe you can call an API, check for some like threshold, certain criteria filtered by certain aspect. But yeah, that's just kind of my high-level thought on those. Yeah. Appreciate the question.
All right. Thank you very much, James. Appreciate your time.
Yeah.
Let's jump on to the next one.